Iterators and generators. Welcome back to the Software Engineering Music Deep Dive into Python. Whether you're a Python developer who's been using for loops and list comprehensions without thinking twice about what's happening under the hood, or you're preparing for technical interviews where deep understanding of iteration patterns can set you apart, today's exploration is going to fundamentally change how you think about one of Python's most elegant and powerful features. Today, we're diving deep into the world of iterators and generators, a topic that sits at the very heart of Python's design philosophy. This isn't just about syntax or cool tricks you can do with yield. We're exploring one of the most sophisticated and beautifully engineered systems in the Python language, the machinery that makes everything from simple for loops to complex asynchronous programming possible. Here's something that might surprise you. When you write for item in my list, you're not just looping through a list. You're actually participating in an elegant multi-step protocol that involves hidden method calls, automatic exception handling, and a carefully orchestrated dance between iterables and iterators. We're going to deconstruct that entire process, step by step. As always, feel free to pause and absorb this material at your own pace. We're covering some sophisticated concepts here, and you'll find additional resources and references in the description below. This is part of our ongoing software engineering deep dive series, where we don't just learn how to use Python, we understand why Python works the way it does, and how those design decisions create the elegant, powerful language we love. Ready to unlock the secrets of Python's iteration machinery and discover the beautiful engineering behind something as simple as a for loop? Let's dive in. Deconstructing the for loop, the hidden machinery. When the Python interpreter encounters a for loop, such as for item in iterable, it does not simply jump from one element to the next. Instead, it initiates a precise multi-step process behind the scenes. First, the loop calls the built-in function iter on the object being looped over, the iterable. This is the universal entry point to the iteration process. The iter function, in turn, invokes the iterable object's special dunder iter method. The sole responsibility of this method is to produce and return an iterator object. Having obtained this iterator, the for loop begins an implicit while-true loop. Within this loop, it calls the built-in function next on the iterator object. The next function then calls the iterator's dunder next method. This method contains the core logic for producing the next value in the sequence and advancing its internal state to prepare for the subsequent call. This cycle of calling next repeats for each element. When the iterator has no more items to provide, its dunder next method is required to raise a stop iteration exception. The for loop's internal machinery is specifically designed to catch this stop iteration exception. It interprets the exception not as an error, but as a signal to terminate the loop gracefully and cleanly. The exception is consumed and does not propagate to the surrounding code. This entire sequence can be performed manually, which makes the for loop's convenience clear. A while loop with a try. Except stop iteration block is the explicit, long-form equivalent of what every for loop does implicitly. The contract, Iterables versus Iterators. The protocol establishes a clear distinction between two roles, the iterable and the iterator. An iterable is an object capable of returning its members one at a time. It is a source of data. Technically, any object that implements a dunder iter method is an iterable. Common examples include built-in sequence types like lists, tuples, and strings, as well as non-sequence types like dictionaries, sets, and file objects. An iterator is the object that actually performs the iteration. It represents a stream of data, maintains the state of the traversal, and produces the values one by one. To be a valid iterator, an object must implement both a dunder iter method and a dunder next method. A helpful analogy is that of a book and a bookmark. The iterable is the book, the complete container of information. The iterator is the bookmark. It doesn't hold the book's content, but it tracks your precise position within it. You can place multiple bookmarks in the same book to track different reading sessions, just as you can create multiple independent iterators from a single list. The why, separating the container from the traversal. This separation of roles is a deliberate and critical design choice. Its primary purpose is to enable re-entrancy, which means that an iterable can be safely and independently traversed multiple times, even concurrently or in nested loops. If an iterable, like a list, were to manage the iteration state itself, for instance, by having a single current index attribute, it would become non-re-entrant. Imagine a nested loop over the same list. The inner loop would advance the current index. When control returned to the outer loop, its position would be lost, leading to incorrect and unpredictable behavior. By mandating that the dunder iter method of a container returns a fresh, new iterator object each time it is called, Python ensures that every for loop receives its own private bookmark. This allows for multiple, non-interfering traversals of the same data source, a fundamental requirement for robust programming. Why are iterators themselves iterable? A subtle but important detail of the protocol is that an iterator must also have a dunder iter method, and this method is expected to simply return self. This can seem redundant, and some have argued it is semantically confusing, akin to saying a driver is drivable. However, this is not a design flaw, but a pragmatic choice that provides protocol unification. By making iterators iterable, Python allows any iterator object to be used in any context that expects an iterable. This simplifies the language and enables powerful patterns. For example, one can partially consume an iterator and then pass the remainder to another function or loop that expects an iterable. Consider this pattern. An iterator is created from a list. My iterator equals iter open parenthesis, my list close parenthesis. Call the built-in next function with my iterator as its argument and store the returned value in first item. The rest of the items are processed in a for loop. Example, for remaining item in my iterator. This final for loop works seamlessly because it can call iter on my iterator. Since the iterator's dunder iter method returns itself, the loop simply continues consuming items from the iterator's current position. Without this rule, the code would be more complex, as one would have to handle the partially consumed iterator differently from a standard iterable. Section 2. The explicit approach. Building class-based iterators. The most direct way to create a custom iterator is to define a class that manually implements the iterator protocol. This approach is more verbose, but offers maximum control and transparency over the iteration's state. The anatomy of a class-based iterator involves three key special methods. The dunder init method serves as the constructor. It is used to set up the iterator's initial state, which typically involves storing a reference to the data source and initializing state tracking variables, such as a counter or index, to their starting values. The dunder iter method is the simplest part of the contract. it must return self, thereby fulfilling the requirement that an iterator is also an iterable. This makes the object directly usable in for loops and other iteration contexts. The dunder next method is where the core iteration logic resides. It is responsible for a sequence of actions on each call. First, it must check its internal state to determine if the iteration has concluded. If there are more items, it computes or retrieves the next value, updates its internal state, e.g., by incrementing an index, and returns the value. If the iteration is finished, it must raise the stop iteration exception to signal completion to the caller. For example, to create an iterator that yields a sequence of numbers, the dunder init method would store the start and end points. The dunder next method would check if the current number has exceeded the end point. If not, it would return the current number and increment it. If it has, it would raise stop iteration. The defining characteristic of this approach is that the iteration state is explicitly managed by the programmer through instance attributes like self.current or self.index. This stands in sharp contrast to the implicit state management provided by generators. While this method requires more boilerplate code, its value becomes apparent when an iterator needs to be more than just a simple data producer. If the iterator object requires its own complex state or needs to expose additional methods beyond dunder next method, e.g., a .rewind method or a .current progress method, the class-based approach provides the necessary flexibility that a generator cannot. Generators as iterator factories. For the vast majority of cases, Python provides a more elegant, concise, and idiomatic way to create iterators. Generators. Generators are a powerful feature that simplifies the creation of iterators by leveraging a special keyword, yield. Introducing yield, the pause button for functions. The yield keyword is the defining feature of a generator. Any function that includes at least one yield statement is automatically transformed by the Python compiler into a generator function. A crucial distinction is that calling a generator function does not execute the code within it. Instead, it acts like a factory, instantly constructing and returning a generator object. This generator object is a complete, stateful iterator that automatically implements the full iterator protocol, dunder iter and dunder next. The actual code inside the generator function only runs when next is called on the generator object that was returned. Yield versus return, a tale of two keywords. The yield keyword is fundamentally different from return. Execution flow. A return statement terminates a function's execution permanently, destroying its local state and stack frame. In contrast, a yield statement pauses the function's execution, returns a value, and meticulously preserves the entire execution context, including all local variables and the exact point of suspension. State. A standard function is stateless between calls. A generator, by virtue of its preserved context, is inherently stateful. It remembers precisely where it left off and the values of its variables. Return value. A regular function returns a specific piece of data. A generator function returns a generator object, which is a ready-to-use iterator. State management, made implicit. The primary advantage of generators is that the Python runtime handles all state management automatically. There is no need to write a class, define a dunder init method, or manually track instance variables like self.index. The state of the generator is implicitly captured in its local variables and its current point of execution. This mechanism is a powerful application of a computer science concept known as a closure. The generator object that is returned closes over the execution frame of the function call that created it, keeping that frame alive in memory. When yield is encountered, Python effectively freezes this stack frame and attaches it to the generator object. When next is called again, the frame is thawed, and execution resumes immediately after the yield statement. This complex process is managed entirely by the interpreter, offering immense convenience to the developer. Table 1. Class-based iterator versus generator function. Use a generator function when you're implementing an iterator that simply needs to yield a sequence of values in a straightforward manner. Generator functions are typically the best tool for most custom iteration needs. They're compact, readable, and Pythonic. Generators manage their internal state implicitly. You don't need to track loop indices or remember where you left off. Each time you call next, Python resumes execution right after the last yield. They're ideal for scenarios like streaming data, one item at a time, parsing lines from a file, recursively walking a tree, modeling infinite or lazily evaluated sequences, e.g., Fibonacci, prime numbers. Use them when the logic is linear and doesn't require maintaining complex or multiple pieces of state. Use a class-based iterator when you need more flexibility and control over the iteration, such as maintaining multiple interacting pieces of state, adding custom methods or properties to your iterator, supporting rewind-reset behavior, or managing external resources. Integrating with frameworks or protocols that expect objects with custom behaviors. A class-based iterator requires you to implement dunder iter and dunder next manually, and often comes with additional boilerplate, like tracking state through instance variables. While more verbose, this approach shines in situations that require a rich object interface beyond just yielding values. Performance, memory, and lazy evaluation. The fundamental reason for using iterators and generators is their efficiency, which is rooted in the principle of lazy evaluation. The power of laziness. Lazy evaluation, also known as call by need, dictates that a value is computed only when it is explicitly requested via a call to next. This has profound implications for performance, particularly memory usage. Because an iterator or generator only produces one item at a time, it does not need to store the entire sequence in memory. It only needs to hold the minimal state required to calculate the next item, 0.15. This memory efficiency is what allows Python to process data sources that are far too large to fit into RAM, such as multi-gigabyte log files, or to work with sequences that are conceptually infinite. The memory footprint of a generator object is constant and very small, regardless of the number of items it can produce, whereas the memory usage of a list grows linearly with its size, 0.15. Generator expressions versus list comprehensions. This principle of lazy evaluation is most clearly demonstrated when comparing list comprehensions with their generator counterparts, generator expressions. A list comprehension, which uses square brackets, is an example of eager evaluation. It iterates through the source iterable immediately, computes every value, and builds a new list in memory to store the entire result at once. For example, open bracket x squared for x in range, 10 close bracket, creates a 10-element list in memory. A generator expression, which uses parentheses, is lazy. It does not compute anything up front. Instead, it creates and returns a generator object that will produce the values on demand, one at a time, as it is iterated over. For example, open parenthesis x squared for x in range. 10 close parenthesis creates a small generator object, not a list. This distinction leads to important performance trade-offs. Memory. Generator expressions are vastly more memory efficient and are the clear choice for large data sets. Reusability. A list is a persistent data structure that can be iterated over multiple times. A generator is a single-use iterator. Once it has been consumed, it is exhausted and cannot be reused. Speed. The performance difference is nuanced. For very large sequences or for operations that may terminate early, e.g., finding the first item that satisfies a condition, generator expressions can be faster because they avoid the upfront cost of building the entire list. However, for small sequences that will be fully iterated, a list comprehension can sometimes be marginally faster because it avoids the function call overhead inherent in the generator's next mechanism. Table 2. List comprehension versus generator expression. Choosing between a list comprehension and a generator expression comes down to whether you need to store all results at once or just iterate over them efficiently. Both are compact syntactic tools for building sequences in Python, but they differ in evaluation strategy, memory footprint, and performance characteristics. Use a list comprehension when you need a fully materialized list, something you'll reuse multiple times, access by index, or pass to APIs that expect a list. The syntax is familiar. Open bracket expression for item in iterable close bracket. Evaluation is eager. Python computes and stores the full list immediately. As a result, memory usage is higher, since all items are in memory at once. List comprehensions are typically faster for small data sets or when you'll iterate over the results multiple times. The return value is a full-fledged list object, supporting slicing, random access, and length checking. This is ideal for pre-computing results to sort, shuffle, or cache, applying multiple passes or transformations, feeding results into list-specific operations like the append method or the sort method. Use a generator expression when you want to process values lazily, one at a time, without holding the entire result in memory. Syntax is almost identical, but uses parentheses. Open parenthesis expression for item in iterable close parenthesis. Evaluation is lazy. Values are produced only when requested. This makes it highly memory efficient, particularly for large data sources or streaming input. Performance shines in single-pass or short-circuiting scenarios, e.g., summing values, checking for the first match, or piping into next, sum, or any. The return value is a generator object, which is an iterator and cannot be reused once exhausted. This is ideal for large datasets where storing everything is impractical, feeding data into pipelines or chained iterator transformations, avoiding upfront computation costs. Real-world scenarios. The benefits of lazy evaluation are not merely theoretical. They are essential in many common programming tasks. Large file processing. When reading a large CSV or log file, using a generator, or the file object itself, which is an iterator, allows the program to process the file line by line. Each line is read into memory, processed, and then discarded, preventing the entire file from being loaded at once. Data streaming. When consuming data from a network API or a message queue, data often arrives as a continuous stream. A generator can yield each piece of data as it becomes available, providing a clean and efficient way to handle the stream. Infinite sequences. Generators make it possible to work with sequences that have no end, such as generating all prime numbers or the Fibonacci sequence. It is impossible to store an infinite list, but a generator can produce values indefinitely. The standard library's Itertools module is built almost entirely on this concept. Advanced generator techniques. Beyond simple iteration, generators possess advanced capabilities that elevate them from data producers to powerful components for building coroutines and managing complex control flows. Two-way communication. The send method. The send method transforms a generator from a one-way data producer into a two-way communication channel, making it a data consumer as well. This is the foundational feature of generator-based coroutines. The key to this mechanism is that yield can be used as an expression, typically on the right side of an assignment. Like so, received value equals yield. When an external caller invokes generator dot, send open parenthesis, data, close, parenthesis, execution of the paused generator resumes. The data object sent by the caller becomes the evaluated result of the yield expression, which is then assigned to the received value variable inside the generator. A critical detail and a common interview gotcha is the need to prime a coroutine. A value cannot be sent to a newly created generator because it is not yet paused at a yield expression. The first call to resume the generator must be either next open parenthesis generator, close parenthesis, or, equivalently, generator dot send open parenthesis, none close parenthesis. This advances the generator's execution to its first yield point, priming it to receive a value on all subsequent send calls. This ability to pause, yield a value, and then be resumed with a new, injected value is the basis for cooperative multitasking. A task, the generator, can run until it needs to wait for an external event, e.g., network IOO, at which point it can yield, passing control to a scheduler. When the event completes, the scheduler can use send to inject the result back into the waiting task, allowing it to resume exactly where it left off. Delegating to sub-generators. Yield from. Before Python 3.3, if a generator needed to yield all the values from a sub-generator, it had to do so with an explicit for loop. For item in sub-generator, yield item. This syntax was not only verbose, but more importantly, it broke the two-way communication channel established by send. The outer generator would have to manually intercept send calls and forward them to the sub-generator, a complex and error-prone task. The yield from expression, introduced in PEP 380, solves this by creating a transparent, bidirectional pipeline to a sub-generator. The statement, yield from sub-generator, automatically handles both yielding values from the sub-generator to the original caller and passing values sent via send into the sub-generator. It provides a clean and robust way to refactor a large, complex generator into smaller, more manageable ones without breaking the coroutine machinery. The evolution to async await. Understanding the history of generators provides crucial context for modern asynchronous programming in Python. Generator-based coroutines, orchestrated by an event loop like the one in the Asyncio library, were the established pattern for concurrency for many years. The async def and await keywords, introduced in Python 3.5, are best understood as a more explicit and robust syntax built upon these foundational generator concepts. An async def function defines a native coroutine. The await keyword is conceptually analogous to yield from. It pauses the execution of the coroutine and passes control back to the event loop, which will resume the coroutine once the awaited task, e.g., a network operation, is complete. This evolution demonstrates that async await was not created in a vacuum. It is the direct descendant of the powerful concurrency patterns first made possible by the yield keyword and its subsequent enhancements. Recognizing this lineage shows a deep appreciation for the language's design philosophy. Common pitfalls. Mastering iterators and generators also involves understanding their common pitfalls and edge cases, which are frequent topics in technical interviews. The cardinal sin: modifying a collection while iterating. Attempting to modify a collection by adding or removing elements while iterating directly over it is a classic error that leads to unpredictable behavior and bugs. The underlying reason for this behavior differs by collection type. For lists, the standard CPython iterator is essentially a simple index counter. If an element is removed, the subsequent elements shift to fill the gap. However, the iterator's index proceeds to the next number, effectively skipping over the element that just moved into the now vacant position. For dictionaries and sets, the situation is more volatile. These collections are implemented with hash tables. Adding or removing an element can trigger a resize of the internal table, which completely invalidates the iterator's current position. To prevent undefined behavior and silent data corruption, these collections are designed to be fail-fast. They detect a change in their size during iteration and immediately raise a runtime error. Safe modification patterns. To safely modify a collection during iteration, several patterns should be used. Iterate over a copy. This is the most common and readable solution for removing elements from a list. By iterating over a shallow copy, the original list can be modified without affecting the iterator, which is traversing a separate, unchanging copy. Build a new collection. Often the cleanest and most Pythonic approach is to create a new collection containing only the desired elements. This is easily accomplished with a for loop, or more concisely, a list comprehension, e.g., new list equals open bracket item for item in old list if condition close bracket. Use a while loop. For complex in-place modifications where creating a copy is undesirable, a while loop with manual index management provides complete control. Since the loop condition length open parenthesis, my list, close, parenthesis is re-evaluated on each iteration, and the index is advanced manually. Additions and removals can be handled safely. The exhaustible nature of iterators. A fundamental characteristic that must always be remembered is that all iterators, including generators and generator expressions, are single-use. They are like a stream that can only flow once. After an iterator has been fully consumed, i.e., it has raised stop iteration, it is permanently exhausted. Any subsequent attempt to get a value from it will simply raise stop iteration again. A common bug arises from forgetting this. For example, if a generator object is passed to the list constructor to create a list, and then the same generator object is passed to the sum function, the sum will be 0. The list call will have already consumed all the values, leaving the generator empty. If the data is needed for multiple passes, one must either create a new generator by calling the generator function again, or store the results of the first pass in a persistent collection, like a list or tuple. That's it for today's video. If you found this content enjoyable, please remember to like and subscribe for more. Good night.